We have been working with accumulation functions in the past several lessons. Here, we're going to work a little bit more closely with their derivatives, and specifically, we're going to learn how to use chain rule with accumulation functions. Okay, so notice this problem, this example here, is asking us to find an expression for the derivative. We have this accumulation function. And let's zero in on the difference. Let's zero in on the new thing. 3x to the third, right? So this upper bound is looking a little bit crazier than what we're used to, right? So previously we'd have functions like this guy g here, an accumulation function that just goes from 1 to x, t squared plus t to the 6th or something like that, dt. And when we took the derivative, so g prime of x, we cancel out the integral. Derivatives and integration are opposite. And we're just going to plug in that x is how we have done it before. So we get x squared plus x to the 6th, and that is our derivative of g. We are going to do the same thing here, but we are going to take a derivative of this upper bound as well and multiply it. So what that looks like, f prime of x, I'm going to plug that in. So 3x to the third squared plus 3x to the third to the 6th, right? So I've done the same thing I've done before. My integral cancels out. I plugged in my upper bound. The derivative of anything where we're plugging in a 1, the derivative of any constant is 0, so we don't have to worry about that still. But now, we are also taking the derivative of this 3x squared. This is also changing. So we're going to multiply by its derivative. So its derivative is going to be 3x to the third, rather, I should say, right? 3x to the third, the derivative of that is 9x squared. So we're going to multiply 9x squared by our result. So that is the chain rule. So chain rule with these accumulation functions applies specifically to that upper bound. So notice I don't need to worry about chain rule. I have a function within a function inside the integral as well. But anything inside the integral, you can think of it as it's sort of protected by this integral. We don't have to worry about the derivative of that, because taking the derivative of this integral is all we're doing, right? So those two things cancel out. This stays unchanged, but when we make this substitution, this 3x to the third is not inside the integral. It is also changing at a rate of 9x squared. So we're multiplying that in there. Now we should simplify these if we can. So notice we have a power to a power. 3 squared is 9, x to the 6th plus 3x to the third. And then we'll just leave it like this. And we'll 9x squared. We don't need to expand that binomial to the 6th power or anything. So that's our derivative. So again, it's just this upper bound that we need to worry about. When that is a function of x besides just plain old x, we need to use chain rule. So you guys are going to have an easy time with these problems. It's good to know how to deal with these, and it's good to get some reps with chain rule, because forgetting chain rule is the most common error on the AP exam that students make. We'll do just one more example so you guys can clearly see the pattern, but like I said, you're going to jump into this easily. So here, where'd it go? Here's our second example. So we're taking the derivative of this accumulation function, and it's the integral of cosine of t squared. So same as before, this is going to get plugged in, and our integral cancels out. We're left with cosine of 2x. Notice that whole thing is being squared because we're plugging 2x in for t, times the derivative of 2x is just x, or just 2 rather, right? So times 2. And then I should simplify that. So 2 cosine the quantity 2x squared is 4x squared. So I've simplified it some. And we're done. So this is the integral, or sorry, this is the derivative of this integral.